Okay, good afternoon. We're going to go ahead and get started here. My name is Ben Follett, and I am the Product Marketing Manager at RISA. RISA is the U.S. reseller of SCIA Engineer, and today we're going to talk a little bit about steel tank design with SCIA Engineer. Before we go ahead and jump into the kind of the meat of the content today, I want to just go over a few items about the GoToWebinar. First, all attendee audio will be muted during the presentation. If you have any questions, please put your questions in the question box. We'll try to answer anything that we can during the presentation, or more than likely what we'll do is we will answer things during the question and answer session afterwards. Finally, if you had some colleagues that weren't able to attend, we will be recording, or we are recording this webinar, and we will be posting on YouTube most likely later today and at the latest tomorrow. Additionally, there'll be a follow-up email that's sent out with because you registered, and in that follow-up email you also get a link to view the recording. And so with that, let's go ahead and jump into kind of the meat of our webinar. So before I get into everything, I want to just kind of introduce the Nemetschek Group. So Nemetschek Group is the larger company that owns all these different software brands that you see, and really Nemetschek has turned a vision into a reality with 15 strong brands focused on developing software for the process of designing, visualizing, building, and managing buildings and building structures as a whole. So really, it's a bunch of softwares that have really one goal in mind. It's to provide best-in-class solutions in the AEC market. And so you may not be familiar with all of these, but certainly are probably familiar with some of the US-based solutions like Bluebeam, SDS2, Vectorworks, and the most recent acquisition, RISA, which was acquired just late last year. Today we're going to focus on talking about SCIA Engineer. SCIA Engineer is a new not a new software, but maybe new in the market, new to you. It's actually 40 years old, and really it is a proven solution that offers really a lot of nice benefits for firms looking to have some more advanced analysis capabilities. And so today, like the webinar invite said, we're going to focus on the modeling, analysis, design of steel tank structures. And so just a brief agenda here. First, we'll obviously spend some time modeling from scratch these steel tank structures using 1D members and shell-based elements. We'll input some loads, wind loads, some hydrostatic fluid loads, some other loads. We'll generate the mesh and set up our analysis for linear, nonlinear, and stability analysis. We'll then review results and evaluate the tank specifically for stability. This is a concern that these kind of open liquid storage tanks have, stability in the buckling of the tank and the tank walls. And then finally, we'll look at some AISC design verification for the 1D members. In addition, we'll take some time to look at the engineering report, just some documentation and some reporting if we have time. So let's go ahead and jump into the presentation here. We're going to spend the vast majority of our time just live demo here. And so I just have a blank version or a blank file. We have kind of the main interface of SCIA Engineer. We have the main service tree, just like a Windows Explorer-like interface. Properties window, which anything we select, we'll see the properties of that object. And then just some standard toolbars and drop-down menus at the top. So the first thing we're going to do is we need to model our tank and the slab that supports the tank. So I'm going to start by just getting a Z view here, and I'm going to go ahead and model in the structure service. I'm just going to model in a slab. And so we'll choose to model in with a plate. In this case, we can choose our material. So I'm just going to go ahead and pick 4,000 PSI concrete. We'll pick a thickness here, so I'll make this 12 inches thick. And go ahead and click OK. Now you can see these drafting tools at the bottom here right above the command line. I could go ahead and use some of these drafting tools, or I could just enter in the points. So I'm going to use the rectangle tool, and I'm going to go ahead and enter in the points. So the first point I'm going to say is negative 60 and 60. Click enter. So we've got our first point. And our second point will then be 60, negative 60. Oops, did something wrong there. So this actually brings up a good point. So if we made a mistake in this case, I can go ahead and select one of the nodes here and see, okay, what exactly did we do wrong here? So 60, negative 60, and here negative 600, 6,060. So I obviously typed in too much here. So negative 60 and 60, And we can go ahead and change this as well to negative 60. And so now we have something a little bit closer to what we want. So negative 60, 60, 60, and this should be 60 there. Okay, so now we have our square here, right? Now we've got our slab. The next thing we're going to do is we're going to put a support under this slab. So I'm going to come under the supports, and one of the support options here is surface and elastic foundation support. So we can go ahead and select that. We can choose our sub from a list, or we can just go ahead and enter in our stiffness here. This is actually a subgrade modulus. This is a kind of your C1Z. This is your case of S factor. So I'm just going to use a flexible stiffness there. So this is a spring, and we'll just apply it here to the bottom of the slab. So now that slab is supported at every element within that slab. Okay, next we're going to go ahead and start to model in the tank. So the first thing I want to do is I'm going to go ahead and just turn off the rendering here, and I'm going to use some sketching tools to kind of sketch the geometry within the tank. So if I go ahead and opening the modeling and drawing, I'm going to click on the line tool, and I'm just going to model in construction lines just like I would if I was in AutoCAD or another software. So I'm going to go ahead and click OK. Again, I'm going to get a Z view here, and I'm going to use the circular tool, and I'm going to go ahead and just model in kind of a tank that we have 50 feet in diameter. That's going to be our tank. So we've got the outline of the tank there. The next thing I want to do is, because I could select this line and make one wall that is the entirety of the tank, but that's really not how tanks are built. And so we have these different shells that we want to, these different segments, the different walls of the tank. So I want to divide this into individual elements. So I'm going to go ahead and actually use the break command to go ahead and break this line into 24 individual segments. So here I have a snap set up that basically is already defined, saying, hey, I want to break any individual line that I have into a certain number of segments. In this case, I chose 24 segments. And so I can go ahead and just choose all those to break those into individual segments. Now when I have those segments created, I can go ahead and use our wall tool. I can choose the material, so I'll choose A36 steel, we'll choose a thickness, and we'll choose a height. And then instead of actually trying to model in these curves, and I'll go ahead and turn off that snap here, I'm going to just use my select line tool and get a Z view again and just grab all the lines to create our walls. And so if I hit escape here, now we've got our wall elements, right? So we can see these walls. We get an isometric view. We have these individual walls that were modeled just by selecting that line. Now the next thing I want to do is I want to add at the intersections here, I want to add a stiffener. And so to do that, I need to add a 1D member. So if I open and expand the 1D member option, I'll choose member. And I don't have any members created. Now I could use something from the profile library, a wide flange or a WT or an angle or something. But in this case, I want to show one of the nice features of SCIA Engineer is the ability to create what we call general cross-sections. And so I'm going to open up the general cross-section editor. And when opening the editor, we see it's just an interface to be able to model whatever we really want. In this case, we can model with polygons or thin-walled shapes. We could pull sections from the library. Or in this case, I'm actually going to use a custom cross-section. And so I'm going to choose to import a DXF or a DWG file. So if I choose that, I can actually navigate then to my file. So I'm going to go ahead on my system here to my webinars folder. We have this. And I have this stiffener. So I'm just going to click open. So this is just an AutoCAD file. It's going to open and it's going to read the DWG file. And so here's the DWG file I have. So it's like a wide flange. I've got this little kind of thing in the web here. I've got these turn downs. I can go ahead and select the curves. So I'm going to select all the edges and I want to connect those curves to define it as one polygon. And then I could set a scale factor, or if my scale was 1:1, which in this case it is, I can just go ahead and import everything. I can next then select a material. So let's call this maybe A992 steel. And then we can bring it into the workspace. So I'm just going to drop it in at the 0 coordinate system. And we can go ahead and see, now we can add to it if we want, or if we're ready, we can click close. And this element is now brought into the library. Now the next thing we need to do is we're going to run a quick analysis, quick finite element analysis to generate its properties so that we can use this in analysis and design. And so I'm going to go ahead and set a mesh size, just that mesh that would do a quick finite element analysis based on a unit load. Click update. And then now here we can see this analysis is happening to generate the properties. And so we get these stress distributions. So these are just some example stress distributions. And then finally, we get all of the properties generated for this particular model or this particular element, including even the torsion and the warping constants, which I know are important in this type of analysis. So now I'm going to go ahead and click OK. I can click OK to close again. Maybe I can rename this. I'll just call this stiffener, and then we'll click close. Now we started that whole process by adding a member. So again, I'm going to go ahead and choose this, and then I'm just going to again select the line tool to get a side view here. Select the line tool to grab all of the edges that I want to apply a line, that element to. Okay, so we've got that element now. Now we can see the first thing that we need to do is that I'm going to run this check structure data tool, and it's because we have two edges here on each side. We have the edge of one slab and the edge of the adjacent, or excuse me, not slab but wall, and the other adjacent wall. So if I run this check structure data, what this is going to do is it's going to find some duplicate members, just basically saying that there's a double member in places that we probably don't want it. The next thing I'm going to do is I want to change the rotation, the local coordinate system of these members. I want them all to be facing towards the middle of this of the tank here. So to do that, I'm going to go ahead and set my LCS to Z by point, and then I can change the coordinates. So that's my 0, 0 system there. So I'm going to change my Z coordinate to 0, my Y coordinate to 0, and my X coordinate to 0. And when we do that now, we can see that all of our members are now have their local coordinate system pointing towards the center of the tank. So they're all aligned the way that we want them to. Additionally, if we wanted to change them too, we could go ahead and select one of the members. I can use a multi-select tool, so I can click on a property and use this select elements by property tool to then say I want all the members to be aligned at their bottom face, right? So now basically they're aligned such that the edge of the member is parallel or is attached to the edge of the tank. Okay, so now that we've got this done here, we can go ahead and I'm going to just connect everything. So I'm just running the connection tool in the software. So this will just generate connections basically where the edge is connected to the slab, where the members are connected to each other. So just necessary for finite element analysis. Now at this point, I've basically got the entire model created, but we do need to go ahead and add some loads. So the first thing we're going to do is I'm going to open up load cases. So we have 4 load cases that I've already pre-created. Self-weight's always created. You have self-weight in the structure at all times. There's no way around that, obviously. You can obviously delete it if you want to evaluate without self-weight, but it's really not applicable. We also have a fluid load created, and I have 2 wind loads created, basically a leeward and a windward wind load that we're going to go ahead and add to this structure. So the first thing I'm going to do is add this load for fluid. So I'm going to go into the load service and choose my fluid load case. So I actually have something in here, so I'm going to go ahead and delete these. So what I want to do here is I want to go ahead and first I want to draw in a load that can then be projected onto the rest of the surfaces. So the first thing I'm going to do is I'm going to go ahead and set my working plane. So I have this working plane that's just a global coordinate system. It's an XY plane. I'm going to set it such that my vertical component is orthogonal to the Y direction. So if I go ahead and choose that, basically now what we get is this Z coordinate now pointing towards the tank walls. And we have this vertical working plane. Now what I can do is I can choose my surface load, and I can do a free surface load. The idea behind a free surface load is it's a surface load that does not have to be uniform. We can vary it in multiple directions, but also can be projected onto any surface in the model. So in this case, I'm going to choose a distribution. We're going to choose a Y distribution. We're going to choose a direction. So in this case, the direction is going to be Z. That direction matches the direction here. The Z coordinate is this blue direction. We're also going to set the magnitude of the load. So we'll set 1.56 and a 0. Finally, we can go ahead and choose our selection. In this case, we want to do a selection based on, we want to select the actual members it's going to be added to. So we'll go ahead and choose that. And then we'll choose our system. Our system will be, in this case, member LCS. And that's how the load is going to be applied to the members that it intersects with. So in this case, it's going to be applied in the member local coordinate system, the Z direction of the member local coordinate system. So I can go ahead and click OK. I can go ahead and start to draw. So I'm just going to go ahead and draw in a rectangle here just by clicking the nodes, just by clicking the snap points. And so the first thing we see is that I need to change the directions here of the magnitude, so I can go ahead and set the bottom magnitude here to 1.56 and the top to 0, and we get our slab here. The next thing I need to do is I need to set my selection. So I'm going to update my 2D member selection. So I'm just going to select the members that I want to apply this load to. We're going to select all of those shells or walls. And then since our validity is selected to all, meaning that this load is going to project in all directions, we can go ahead and click to generate the load. When we generate the load, we can see we get this load now, this fluid load, pushing out on the structure surface. And so because of our direction set, because of the magnitude set, we get that outward pushing system. Now we could have done something very similar. We could have reversed the sign of the load to a minus 1.56, and we would have gotten the load pushing inward. So we could have done the same thing if we wanted to achieve a soil load, for instance. In addition, I need to apply a load for this fluid load on the bottom of the slab here. And so again, I'm going to go ahead and use the free surface load. In this case, I'm not going to do a variable load. I'm just going to do a uniform load. It's going to be in the global system, and then it's just going to be a negative 1.56. And I'm going to go ahead and make it a circular load. So we'll go ahead and let's get our working plane back. So I'll go to UCS and global coordinate system. And we're going to go ahead and just model in this load downward. So we've just got this downward force now that's acting on the slab. So now we have our fluid load set. We have two more loads that we need to create. The first, and they're both going to be wind loads. So I'm going to go ahead and switch to our positive wind load. And to create our positive wind load, the first thing we want to do is we need to again move the working plane. And so I want to set up a working plane that's outside of the tank that represents where that wind would be coming from effectively. So again, I'm going to go to Tools and UCS, but instead of trying to set the UCS, I'm going to use the UCS Manager. So I've already preset some UCS. So we can see here I've created a UCS for the positive wind load at 50x, 0y, and 12.5z. So if I click OK, we're going to get that load, or we're going to get that established here. So we can see that here. I can change my direction here so I have it vertical, and then we can start to model our load on the tank. So I'm going to go ahead and again choose a free surface load. Now in this case I can choose our free surface load to be maybe in this case a uniform pressure. So I'll say it's going to be a 0.03 kips per square feet. So this is just our wind load. I can also set what's called a validity. So I can choose a validity that says I don't want to choose this load to be applied to the entire structure. I want it to be from a certain point to another point. So I'm going to say it's from negative 50 to 0 in this case. And then we can choose the direction that we want to apply. I'm going to choose the load LCS. So then if I just look at a view that's perpendicular to my system here, I can go ahead and draw in my load. So again, I'm just using the snap points. And we create our load. So let's go ahead and see the load we created here. So we've got this load, and then again, if we go ahead and project the load, if we go ahead and generate the load, let's see what we get here. We get this load generated. Now we can see again, just from a little trial and error here, we have the load generating in the wrong direction. If we need to switch that, we can just delete the generated load and go ahead and switch the direction. So I'll just make this a negative and then generate the load. So we can see here we've got this load applied to these kind of first half of the shell elements, the wall elements, in the direction that the load's applied. So this is that windward load that we want. Now next, we want to do something very similar for the leeward load. So I'm going to go ahead and switch to this negative wind. And again, I'm going to go ahead into my Tools, UCS, and I'm going to open up the UCS Manager, and I'm going to choose that negative wind direction. So here again, we have that negative wind direction. Again, I'll get a view that's perpendicular, and I'm going to go ahead and bring up a free surface load. We'll set a different validity here. We're not going to go from negative 50. We'll go from 0 to a positive 50. And we're going to go ahead and choose a similar load. So we'll do this 30 kips per, 30 pounds a square foot. We'll also select our selection to be auto again. And we'll go ahead and change this. We don't want this to be applied. This windward load isn't going to be applied in the direction of the load, but actually, again, just like the fluid load, it's going to be applied in the direction of the member, so the member LCS. So again, we can use our snap points to model in the load. So we've got the load now applied. Now we can go ahead and generate the load. So if we choose to generate the load, we've got a load now that is pushing out, just like the fluid, but it's pushing out. So it's kind of that load that's the windward load as we see it. That leeward load is blowing on the tank here, and then on the back half of the tank, it's actually kind of pulling the tank out. And so that's the load interaction that we're going to have. Okay. So now we've got all of the loads applied to the structure that we need. I'm going to go ahead and close our load service, and we can go ahead and before we talk about creating load combinations, we can go ahead and look at creating or look up setting up our model for meshing and the analysis. And so the first thing I'm going to do is I'm going to open up the mesh setup. So generically we have an average size of 2D element, so we have a 3-foot global mesh. That's just going to be set all the time. That'll be, we can change that, make that whatever you want, and then we can also refine the mesh as we see fit. We also have the ability, like I said, to do local mesh refinement. So if we look at local mesh refinement, I can go ahead and say I want to do maybe a 2D member edge refinement. So I want to apply maybe a refinement at the location where these walls meet this tank, right? And so maybe I'll go ahead and select the base of the walls here, and I can apply those mesh refinements. And so those mesh refinements are just going to get applied based on a based on this kind of attribute here. So there's just this yellow attribute. We could also go ahead, I'm going to make my UCS back here. We can also go ahead and apply a surface mesh refinement, 2 feet again, to maybe the slab or something like that, right? So we have the meshing that we want. If we want to get rid of these viewables, we can go ahead into the view parameters and just turn off our refinements. So now they're just hidden. The attributes of those are just hidden. The next thing we can do is we can look at our solver setup. Now I have enabled in this particular project nonlinearity and stability. They're the other analysis types that we're going to look at in this particular case. And so for a standard nonlinear analysis, we're going to use a certain type of nonlinear solver, the Newton-Raphson method. So if you're interested in that particular method, we can send you some information about exactly how SCIA is doing it. We're also going to use a certain stability solver. So these are very similar to how the software does dynamics. Essentially, it's creating eigenmodes. Eigenmodes in this case are just for the number of critical values that it will create for stability. And we'll go ahead and see exactly what those critical values mean when we go ahead and look at the results of stability. And so now we can go ahead and make sure that our combinations are set up properly. So if I open up combinations, I've created 2 just kind of global envelope-based combinations, so an ultimate limit state, so an LRFD strength base, and then basically a serviceability state combination. I'm going to go ahead though and create 2 just kind of linear combinations. First one I'm going to go ahead and call dead plus fluid plus 0.6 wind. And I'm just going to make it a linearly ultimate combination. And we can go ahead and click OK. And then I can come into the table here and change the factors if I need to. So for wind, I can make this 0.6, 0.6. Then I'll create a second new combination with everything in it. And we'll call this one 0.6 dead plus 0.6 wind. And again, we don't want fluid in that, so if we needed to edit it, we can go ahead and delete that out, and then go ahead and just change the factors again. So 0.6 on self-weight and on the 2 winds. So now we have those 2 combinations. Additionally, we can go into the nonlinear combinations, and we can either create our combinations from scratch, or if I click cancel, we can create new from linear. So we can just go ahead and pick the 2 linear combinations and say, hey, we want those to be looked at for nonlinear. And then the same thing with stability. We can come in here, create our own from scratch, or just say, hey, I want new from linear, and do that the same way, creating our stability combinations that will match identically to our combinations for linear. Okay, so it's at this point we've got our linear combinations set up, we've got our nonlinear combinations set up, we've got our stability combinations set up, we've got our mesh set to the way that we want the mesh to be set up, we've got the solver setup created, we've got the loads applied, we're ready to run an analysis. Now I'm not going to waste the time to spend running the analysis. We'll actually run one a bit later in the webinar. But for this sake, I'm going to go ahead and just switch to a second file, which already has the results run. So in this particular model, it's the same model that we had already had. You can see here we have the mesh already generated, so you can see a 2-foot mesh on the tank walls. You can see a 3-foot mesh, so it's a slightly larger mesh here on the floor or on the slab that supports it. You can also see here that we've got this. We do have a refinement along this edge to make sure that we have some really nice interaction between the mesh elements here and the mesh elements on the slab. So now we can go ahead and look at some results. So in the service tree here, I'm going to click on results. And the first thing I'm going to do is just open up 2D member results. Let's just look at a simple result for, say, contact stresses. So I can choose contact stresses and look at our global result. So here we can see kind of the contact stresses that we have here. So generally we have somewhere between 2,000 and 2,400 PSF on this slab. You can see obvious out here we don't really have anything. There are some cases where it's giving us some negative. If we needed to, we could actually run a nonlinear analysis and do a nonlinear subsoil analysis to get rid of any negative. But in this case, since it's only one element, we're not too worried about that. So we can look at those contact stresses. We can also look at 1D member results. So if I go ahead under beams here, we can choose internal forces 1D members. And we can choose maybe for a nonlinear combination, look at the values, the axial values. So we can see here the different axial values in those members that we're getting. This is showing us a global result, so it's showing us every member. And so we can see exactly what we need. If I want to, I can go ahead and look at the table results. So this table result is just going to give us whatever is the results that are shown graphically, so all those members. It's giving us the worst case of each type of result, so worst case axial, shear, moment, etc. We can go ahead and modify this. This is just like an Excel file. We can go ahead and modify this as we see fit, or we can just go ahead and choose to export this to Excel if we really wanted to. So this is just a one-button click. If we wanted this table, I can physically just click Excel, and it's going to go ahead and just very quickly launch Excel. It's actually launching it on my second screen here. I'll just drag it over, and it's just creating that table for us so that if we need to do any post-processing in Excel, we can do that as we see fit. Okay, so now let's go ahead and look at some stability results. So we ran a linear, we ran a nonlinear combination, but we really need to look at the stability results. And so when looking at stability results, there's two things that are really important. The first is the critical load coefficients. So if I go ahead and select critical load coefficients, I'm going to get a window here that shows us the critical load coefficients. If you remember correctly, stability combination S1 is the combination which has dead, fluid, and then the 0.6 wind. Stability combination S2 is what has dead and 0.6 dead plus 0.6 wind in it. And so what we can see here is that in the first critical mode, or the first eigenmode, we get some buckling at 91% of the load applied. So this means that when we have a critical load coefficient below 1.0, we have buckling, that the structure is going to buckle under those conditions. And so in this case, we have two specific modes, if you will, in which we'll see buckling. So the next thing, not only the critical load coefficients, we can go ahead and look at these critical load coefficients in a 3D displacement. So we can choose to look at our stability combinations and choose that first or that second stability combination first mode, which has a critical load coefficient of 0.91, and we can refresh the results. And so we can see exactly what's going on here. So this is how the structure is going to buckle under 91% of the load applied for 0.6 dead plus 0.6 wind. This is what we're seeing here. This is exactly what the software is telling us. We can also go ahead and look at the second combination. This is where we're going to buckle under 99% of the load, so we just get a slightly different buckling behavior. So because of this, what this tells us is that we need to, in some way, strengthen the system so that we no longer get this buckling. And there's been all kinds of studies and information done on this, and it's essentially in this tank structure why we apply a wind girt to the top of the structure. And so that's exactly what we're going to do. So let's go ahead and close out of our results. And I'm going to go into the structure service, 1D member, and choose member. And I already have an angle that I've applied here. So I already have an angle that we've predefined here. And so I'm just going to choose to use that angle as my stiffener. I'm going to set a rotation for that so that we can get it oriented in the correct fashion. And I'm going to go ahead and click OK. And just like we did before, I'm going to go ahead and use that select line tool. I'm just going to grab the edges on top of the tank. So we have the edges on the top of the tank. We can kind of zoom in here and we can see exactly how this is oriented. So we can see how this angle is oriented. We could change it if we needed to, but in this case we don't. I'm going to go ahead, because we just added new members, I'm going to run this connection tool just to make sure that everything is reconnected properly. And then I'm going to go ahead and generate the mesh. So very quickly we can click the mesh generation. And so this mesh is just going to generate all the mesh elements based on our preset values. So 2 feet at the walls, 3 feet at the tanks, or 3 feet at the tank floor, so we can see that. And now we can go ahead and rerun the analysis. So I'm going to click on the calculation button. Here we can see our basic setup. I'm going to see we have a linear, nonlinear, and stability analysis. We're going to run these all at the same time. So I'm just going to go ahead and click calculate. And so when this starts here, we already did the mesh generation, so the task queue viewer tells us that. And then it first obviously generates our static loads and load cases and combinations. Secondly, it jumps into, if you remember in our solver setup, we chose our eigenvalue solver type. So we chose a polynomial solver type. That's an internal solver that we at SCIA created. And that's what's running our 8 different eigenmodes, or our 8 different critical values. And so since we have 2 load cases, it's going to jump into that characteristic polynomial solver twice, and it's going to run each of the critical values. So we'll have 16 total critical values because we're doing it in 2 load combinations. Once the stability combination is complete, and we can see everything that's going on in this calculation, we're going to go ahead and jump into the nonlinear calculation. We're just going to see a really quick little iteration. It converges very quickly, so there's almost nothing to look at. And then finally, we'll get just a basic overview of the results. So we can see here, hey, we've got our maximum information for linear, and then our maximum information for the nonlinear combination, what methods we use, whether or not the linear stability was successful or not. So now we have results that we can again use with now these wind girts in play. So now with the new results, we can go into the results service again, and we can go ahead and look at our critical load coefficients. So remember, we had critical load coefficients at 0.91 and 0.99. We now have, in the same exact eigenmodes, we have load coefficients at 2.7 and 3.02. So now we're going to experience buckling under 2.7 times the load and 3.02 times the load. So in this case, we basically proven we don't have a buckling issue anymore because we added those wind girts. We can also see this in the displacement. So we choose the displacement, and we can come into that first mode again. And we're no longer getting the same buckling behavior because we've kind of restrained the top here. We strengthened the top. We're now just kind of getting this intermediate localized buckling in the plates between the stiffeners. Now, one thing I didn't mention before, but if we wanted to do this, we can always choose view and view the model in an animation window. And we can always choose to animate this particular deflection if we want to. So we're just going to get an animation here if we choose to just kind of look at this if you so want. Okay, the other thing that we need to look at, now that we've kind of recognized things for linear, we looked at nonlinear, we feel good about where things are from a stability standpoint, we can go ahead and, again, leave the results, and we can go into the steel service. And so in the steel service, we're going to go ahead and just run a steel design. We're just going to use our ultimate limit state combination, and we're going to run a design of these general cross sections. Remember, if we turn on the rendering here, these cross sections that we created that have this these lips here and this little nub on the web. So I'm going to go ahead and click refresh. And you can see here now we've generated a unit. This is actually drawing the unity check on all the members. So we're drawing it on all the angles at the top and all the stiffeners. We can create we can change the scale real quick just to kind of see differently what's happening. We can also find the worst case one here. So in this case, we're getting a worst case for each cross section. We can go ahead and view this. So first I'll just choose a brief output. We can view this in a table. And so we see here that for the stiffener, we've got a worst case, B90 is our worst case member, and we've got an 83% unity check. And for our angles, we have a 56% unity check. We can go ahead and see that in more detail by switching to detailed. Again, clicking refresh, and I'll just click preview again. And now we're going to get a detailed output. So in this case, we're going to see per AISC 36010, we're going to go ahead and see that we have an 83% unity, and we can see what's going on for this particular member. So here's our classification of, it's a non-slender section. Here are the loads in that particular member. Here's the buckling check, the torsional check, the strong axis bending, weak axis bending, all this stuff which gets us down to that 83%. It also will check torsion to see if that controls. It doesn't in this particular case, and then it'll move on to the next member type. So in this case, we're moving on to that angle type. So this is then validating our steel code check for all the checks that we need to do according to code. Now at this point, we're ready to kind of complete the design, and the best way to do that is using what we call the engineering report. So I'm going to go ahead and launch the engineering report manager. So the engineering report, and if I open up this particular report, the engineering report is a separate report that's a separate executable that is available for you to do reporting in SCIA Engineer. So the beauty of this is that because it's a separate executable, you don't have any you don't have to only report things while you're doing reporting things, or only do model things while you're doing model things. The nice thing about this is these two work together. And so you can see I can be in the model at the same time as I can be in the report. And so what's great about that is that changes in the model are then reflected in the report. We get these notifications that say, hey, something is out of date. We need to find out what it is, or we need to update or regenerate this particular model. So let's go ahead and bring a few different things in. So I'm going to go ahead and go back to our results and choose our 3D displacement. I'm just going to choose our displacement to match this one. And so let's go ahead and go into this first mode here. So we've got the displacement. So we want to put this, and we can change the scale here. We don't need this scale to be so drastic. We can go send this to the engineering report. So I'm just going to right click and say live picture into engineering report. We're going to be presented with a window about this particular picture in which we want to set some of the settings. And so we can go ahead and set some of those settings. I'll choose I want to fit to page width, and I want to insert it into the inbox, or I just want to insert it into the report. I'm just going to insert it and close. So I'll just drop it into the report. So I click insert and close, and then if I go into the report's just going to bring in information in from the data, so we can see the task manager just bringing in that information, and it's going to drop it right into our navigator, which is essentially our table of contents. And so we've got that picture then. So we've got that picture information. We can also go ahead and bring in different results. So we can either bring in the results directly from the model, or here in the available items list, we can go ahead to say results. Maybe we'll look at contact stresses, so just by double clicking here, and choose for a specific combination maybe, and we'll choose the way we want to look at this, and we can just go ahead and click regenerate. And so this is going to give us that table. So it gives us that table to say, okay, here's what we have. This is the maximum contact stresses for this particular case, right? So we've got this max contact stress, right? So we have that information. We can also bring in the steel code check. So if I go ahead and look at steel, we can bring in our check of LRFD. That's the check that we had done. So just go ahead and double click on that. And again, set the information. So we'll choose our combination again. So we want the ultimate limit state combination. And we can choose a brief report. I want to show maybe for every member. I want to show them on the brief report. Just hit refresh. And then we can see a table of every member here. All the general cross sections with their unity check values, and all the angles with their unity check values. And so we can build a report very easily that works with the model. The other thing that you can do here is you can see that these elements are out of date. And they're out of date because I've actually locked them. And so here we're actually seeing multiple runs of the model, multiple different versions of the model, and the results that we're accustomed to, that were assigned with that. So here we can see that first picture here that has the deflection without the wind girds, right? And so this is that deflection that we saw without the wind girds compared to the deflection that we see with the wind girds. And so we can do that by just choosing this lock button here in the navigator. And so this allows us to do some value engineering, or gives us the ability to do multiple runs of the model, or multiple different sets of results in the same model without having to create different models, and being able to create that all in one space. The other thing that's really nice here is that because this is fully automated and we have all this information that you can create, whether it's input or output, you can actually create your own separate templates. So let's say that you were doing a tank and you had results that were very similar for every job that you did, and you wanted to have those reports all set up the same way. You could set up your reports with certain headers and footers and table of contents and certain pictures and certain other formatted text and information, you know, a list of cross sections, certain results, and then you could actually save that as a template. So we could save that as a template for your use again and again. And so when you have that, then you would just have the ability to go here all the way at the bottom and choose report templates. So I don't have any user templates set up in this particular case, but we do have some system templates that are created, and you can, but this is where your user templates would show up. And so then instead of creating this from scratch each and every time, you would just come down here, you would choose your particular report template, and it would populate the navigator, and then you would regenerate. Now, one last thing, because again, like I said, this is dynamic, if we were to change something in the model, if we were to come in here and say, hey, I want to change the size of the stiffeners, or I want to change the size of the angle on top because, you know, the max unity for that angle was only, you know, 56%. I want something a little bit smaller to save some steel. Once we make that change in the model, we're going to get these in the tables here. All of these results that are unlocked are going to show that they're out of date. And because they're live, because this is a live picture and these are live tables, we're going to be able to regenerate them and just pull new information from the model. And so it's dynamic in this way that you don't just have to wait till the very end to set up a report and then, you know, when you make changes, create another new report, and then make changes, create another new report. Because this can work dynamically, it just gives you a much better workflow and much better kind of seamless transition between what you're doing on the engineering side and then when you have to create your documentation. Okay, so just kind of a recap on the agenda here. You know, we looked at some modeling of steel tank members, 1D members in the shells, the tank slab with the elastic foundation support under it. We created some loading conditions, wind, hydrostatic load. We talked a little bit about if we wanted to create a soil load on the outside, we could do that as well. We generated the mesh and ran our linear, nonlinear, and stability analysis. We reviewed the results and evaluated the tank for stability considerations. And finally, we looked at some AISC design verification for the 1D members, including that general cross-section, and looked at all that information in the engineering report. And so with that, I want to open up the floor to some questions. So I'm going to go ahead. If you have questions, go ahead and put it in the questions tab, and we'll go ahead and answer as much as we can in the next few minutes. So we've already got quite a few questions here. So I'm going to go ahead and start looking here. So we have a question about preloaded code-compliant design loads. So we do have some code-compliant design loads, mainly for lateral loading per ASCE for wind and seismic loading. So you can, we do have a wind load generator. We do have a seismic load generator that that you can utilize that exists, that you could apply to this tank without any issues. There's a question about, is there a way to apply the real, sorry, we got questions coming in all over the place. Is there a way to apply real load distribution over the cylinder instead of a uniform pressure? Certainly. I mean, what we had done there is we have a linearly varying load distribution. And so for instance, for that wind load, we didn't have to make it a uniform pressure. We could have done a linearly varying pressure if we wanted to. We also have the ability to use what's called, we can set up our own wind load curves if we're using the 3D generator, and we can make a stepped system. So, you know, for 0 to 10 feet, it's this pressure. For 10 feet to 20 feet, it's this pressure. We can create that and use that in the 3D wind load generator. We don't have the functions that we have. There's a question about meshing. The functions that we have for meshing, we do have something what's called the automatic mesh refinement. And so essentially what that means is that it'll allow us to allow the system, instead of doing our own refinement, it'll allow the system to review the results in adjacent mesh elements and determine the accuracy of the mesh for your loads applied. And so you choose load cases that you want to evaluate the mesh for, and then you run the analysis, and then SCIA will both tell you the error that exists in your model and then propose for you a mesh refinement. And there's some tools there that kind of tell you when your mesh is basically good enough, because you could always just continue to refine and refine and refine. But that helps take the guesswork out of meshing. Let's see. So we got a question about some foundations. So we do have, you can model foundations, so you can model piles with skin friction on the piles and stuff like that. We don't currently do the design of those piles. If you're interested in pile design and stuff like that, that's something that RISA Foundation would be very good at. And so if you're interested in that, we can certainly, you can contact us and we can send you some information about RISA Foundation. There's a question about some composite tanks. You know, you can model tanks out of any type of material. And in this case, we just chose to use steel tanks. If they needed to be, you know, plastic, you could create a plastic material and model it that way. If they needed to be cold form or concrete, you can model it that way. If it needed to be a, you know, a certain, you know, you can use something called property modifiers to modify the stiffness of the walls. If you had something like a fiber reinforced concrete or something, you could do that. I mean, it's totally up to you. And this was just one example of a tank structure that we can handle. Let's see what else. So there's some questions about buckling. So in this particular case, you know, we have the 1D members that act as the stiffeners. Buckling is going to be defined based on where things are connected to those members. So in that case, for the strong and the weak axis, we may have had their overall lengths, their total lengths, 25 feet being their unbraced length, or but we could also evaluate them to say that the shell that connects into them braces them in certain directions. So we could say, maybe we would say in this case, because it's the top flange of the member is connected to the tank wall, that the top flange is braced for lateral torsional buckling or something like that along the length, so that we could set that unbraced length then to essentially be 0 in that case, and then for an unbraced length for the lateral torsional buckling, we'd have something that's 0, not 25%. So we can take, or 25 feet, we can take into account the fact that we do have different elements framing into it, whether they're 1D members or 2D members when it comes to buckling. We don't have checks, design checks on the plates itself. One of the things that we do have, and we've seen some of our customers do, is we do have a solution which we call SCIA design forms. Essentially, it's like it's a scripting environment that allows you to create your own checks and actually basically attach them to the software. So basically, imagine it's basically like a MathCAD-like interface where you could do some very brief programming. You could pull results and information from the model to help create that check, and then basically you just establish the check within the interface. And so basically what happens now is you could create a very simple plate buckling check or a plate steel check in the model that can run each and every time based on the way that you do it, maybe in a spreadsheet or something like that. And that would now be integrated into the software, into your version of the software, and you could use it each and every time. You could run the check just like I ran the steel code check. You could insert it into the engineering report just like I did. It basically just comes like an internal check then, and it's just something that you build and you maintain and you manage. And so we have that interface available, and it's just part of the software that you can use if that's something that you desire. So someone said, can a steel floor be modeled to sit on top of the concrete mat? Sure. I mean, it's just a matter of modeling in that case, you know, whether you want to model it as a steel floor with, you know, they're kind of integrated into each other. We would use something called a subregion in that case, basically to say, okay, I have a 12-inch slab, but then the top 2 inches or the top 1 inch or whatever is a steel plate, and maybe it's a steel plate over the entire thing, or maybe it's just a steel plate in the in the portion of the tank. We could do that. That's no problem. And then obviously the software in that case would understand that we have a variable material, and we also have, you know, so that would give us variable stresses, variable deflections, stuff like that. So it would understand that when we use a subregion. So let's see, what else do we have here? Let's see. In this particular model, this is an open steel tank, but you can very easily, we could put a roof on it. We could put a conical roof on it. We could do hopper structures. We have people doing that. It's really up to you. I mean, this was just an, you know, for a simple example, in this particular model, an open top steel tank. We don't have any generators for hydrostatic loading, and everything that we have here is based on AISC code or ASCE code. We don't have any of the AWWA codes built in, but that doesn't mean that you can't create load combinations and save those or set your standards in a template for those codes if you need them. Obviously, if you put a top on the structure, it would certainly affect the loading of the structure. Obviously, you'd have loads on the roof. You also probably wouldn't need to put in the wind girts because the roof structure would be bracing the load or the top of the wall. So all those things would come into account when you're doing the analysis and the design. As far as seismic loads are concerned, you can generate seismic loads based on any code. Mainly in this case, we're talking about the ASCE code. So you could do a true blue dynamic analysis where you're adding, you're not quite, you don't really have the need to do an equivalent lateral force analysis for a tank, but you probably should do more of a modal response spectrum analysis, and you can do that. Basically just taking the mass of the structure and allowing the load to be generated. And so that's not a problem. You can generate it in multiple directions, and you can create the seismic load combinations per ASCE if you need to, and you set up your seismic response spectrum based on the provisions of the ASCE code. That's no problem at all. As far as a concrete tank, asking about reinforcement, you can look at the reinforcement in a concrete tank. If you had a cylindrical concrete tank, you could look at the reinforcement required in that. So it would give you reinforcement at 4 different levels, basically top and bottom, inside and outside face. In both directions, it would tell you the area of reinforcement that you were needed. You could add openings and stuff like that and see the area of reinforcement you were needed based on the codes. That's certainly possible. Let's see. Somebody just asked a generic question. The webinar, again, will be recorded. It is being recorded, and so as soon as we clean it up a little bit, we'll be posting it on our YouTube. And if you registered for the webinar, you will get an email tomorrow that has the recording in the in the body of the email, so you'll be able to see that no problem. Let's see. Is there any other questions here? I think that's about it. Obviously, if there's more questions that you have, please feel free to contact us directly. My email is very simple. It's just Ben F, the first initial of my last name, at risa.com. You can contact me directly. We'll also be sending out the webinar certificates, so those will go out this afternoon as soon as everything kind of gets finalized. We'll put that list together and we will send out the certificates, so you'll get those in your email probably by the end of the day today. Additionally, like I said, if you have any questions, please feel free to send an email. You also can look for a tryout of SCIA Engineer. We have a free 30-day tryout. It's a full-blown version of the software. Just go to scia.net, SCIA.net, and right there on the front page, there's just a button that you can click for free tryout. Just fill in the information, and then the tryout will be sent to you. Also, if you're interested in more kind of in-depth look at the software, we can certainly set up a web demo similar to how we're doing this now, where we can talk about maybe what you're specific to your business and show you maybe how SCIA can be helpful doing some of these advanced analysis criteria concerning tanks. With that, I thank you for your attendance today and your participation. We had a lot of really great questions. Like I said, we'll be posting the webinar on YouTube. I'm going to put all of that on later today. And if you have any other questions, please don't hesitate to send me an email. Otherwise, thanks very much, and I hope you have a great rest of your day. Bye-bye.